Yes, go ahead.
Does he have to
Yes.
introduce again?
Yes, please.
Bambu, can you introduce again? Sorry.
Yeah, sure. Hello everyone. I'm myself Anbarasan, and Osman and myself have worked through the sequences and series of functions in this program. And Osman will present with the various project example of a non-differentiable function. Over to you, Osman.
Thank you, Bambu, for introduction. Hello, everyone. Today we are going to talk about the special function of Weierstrass's non-differential function. And let me give you the outline. We will first mention about the history of this, how developed, how construct, and what happened during that days. And then we will move on to the sequence of functions, give some basic definitions, as well as the series of functions. Then finally, we go through the non-differentiable of Weierstrass function. So, in the early, after the development of calculus, mathematicians think that if a function is continuous on some domain, that it should be also differentiable, not every point on the domain, but at least a finite number of points. In 1806, the French physicist and mathematician Andrew Mirambet had even published a proof about this claim, but later on it will be disproven by Weierstrass in 1872. He developed a function that is nowhere differentiable, which caused a shock and a panic, also a scare, to be honest, among the mathematicians at that time. And this is the function here given under some certain conditions. There's a big quote about it. Hermit letter the Stildes. I turn away with fear and horror from the lamentable plug of continuous functions which do not have derivatives. So let me define the sequence of functions first. Basically, this is a sequence, but the elements of all are functions. And here is a little example here. We will define two types of convergence. Let's go ahead. The first one is pointwise convergence. We say that the sequence of functions converges pointwise to some function f if this limit holds. And now we will introduce a stronger convergence, which is uniform convergence. And we again define a sequence of functions, and we need a positive epsilon, and there exists a big enough number n in natural numbers, which is natural numbers. This difference must be less than epsilon if we have a big enough n. So in here, we don't want every element of sequence to be hold this inequality. We just need some big enough n for this. Then we say that this sequence uniformly converges to f. Yeah. Now there is some lemma which we will use on our proof. So if we have a sequence of continuous functions this time, and if they converge uniformly on the domain to f, then we say that f preserves this information to be continuous on A. So we don't lose information here. It's a good lemma. So the general intuition is that if we want this information also don't to be lost, but this doesn't have to be always like that. If a sequence of functions approach to the f, and we want that f prime of n also converges to f prime of x, but this is not always true because we need stronger conditions, and two functions can be close to each other, yet their different derivatives can differ significantly. Therefore, we need to define a more stronger condition about it. Let us define now. If we have a differentiable sequence of functions here, we need this sequence converge pointwise to some function f, and we need also f prime of n also converges to some function g, but this time we need also uniformly converges in its derivative, and then we say that f is differentiable and f prime is equal to g. So here is the definition of a series of functions. We define it as the sequence of functions, as a term of sequence of functions. If this series, we got this series, then we call this as a series of functions. So let us define the convergence of series of functions. And first we define a partial sequence of partial sums of the series of the functions, this is the whole series. If you want this partial sum converge pointwise to S, we need this limit holds again. And if we want it to uniformly to S, we need the same epsilon definition again. But here I'll just give it like that way. So this is a nice convergence test. In this content, it's very useful, and this sequence of functions we generally use to prove its convergence uniformly. Weierstrass himself developed it. So we need a sequence of functions, of course, and we need this time an upper bound, a real number, non-negative upper bound. And for each of this sequence of functions to be bound up, need to be bounded by above, also lower, but we don't need it. And we want this bounds to be in the series to be convergent also. Then we say that this series converges uniformly omega. So this is a geometric visualization of our function under some conditions. Now let us look a bit closer to the function. Here, notice that even if we get closer, this zigzags and the sharpness points are still follow the same pattern and remains the same. The function, even if you get closer and closer, you always will see this sharpness and this zigzag over here. There is not even a straight line segment here in any interval. You can find it. You can also geometrically show non-differentiable of it, but we also prove it by theoretically. So I will now show this convergence of the Weierstrass function under these assumptions. Let us prove it. We pick a real number within A, between 0 and 1, and we want B an open integer which is greater than 1. We will use the M test here. So we need an upper bound for this sequence of functions. Since this a to the power of n is positive, we can take it outside, and since cosine function bounded by 1 above, we can just write this. And since this is a geometric series over here, we also know it's convergent. So we can say by M tested, that function is continuous uniformly on real line, and since our lemma we know it's also continuous. Because here this is convergent and cosine function is continuous everywhere, so we can say that Weierstrass function is also continuous. So now we will prove the non-differentiability of this function. Here this condition today restricted to the only a b greater than or equal to 1, but this is the one Weierstrass proved in the bracket today. We will do his same proof. But we will sketch it because it's a very long proof, which we don't have the time here, and I don't want to bore you all. So let us pick an arbitrary real number. Let's say x to 0 and a natural number m. Now consider this neighborhood. We want Cm to be an integer. We pick as it an integer on this neighborhood. I will prove this theorem as in 3 cases, and this one will be the case 1. We construct little things here, and we choose x of m as follows. Now, after we do some calculations, we get this inequality here, and we can take the limit and using squeeze lemma as m goes to infinity, the limit xm approaches x0. Now consider the difference over here. We'll call it a plus y. So what is a and b? Here a is a finite partial sum, and b is as follows. Now case 2 is the finding an upper bound for A, and case 3 is the finding a lower bound for B. You will see why later. And so after doing some operations in the finite sum and using trigonometric identities and triangle inequality, we get this boundary for A. Also, since this is a finite sum, we know this is also convergent, and we go to the next step. Since we know all those, and we finally get a desired upper bound for A. Now for B, it's a little bit harder, a longer algebras needed. So we use our definitions in the first case, and using this nice identity of cosine function, we get this equality here, and we substitute it and doing more calculations again, we finally get a lower one for B, as here. So therefore, again, by substituting the definitions of above inequality, we get this inequality here. So by multiplying both sides by a to the power n, we finally get a nice lower bound for absolute B this time. You can see here. Now, by using reverse triangle equality, we get an lower bound for this difference here. And since this is bigger than 0, I mean positive, this difference quotient will become like this, and this is our desired epsilon. So we just need one epsilon to show this is divergent, and here we use this absolute value to prove our first assumption here. And since we found our positive epsilon, we can now say that this limit is divergent, and we know this goes to x0 as m goes to infinity also here. So which proves that our function is nowhere differentiable, and since this is also arbitrary real number, the proof is done here. So if you're interested more on this topic, I will suggest you to read this table. There is lots of functions also, like these functions here. And thank you for your attention.